Okay, adding vectors by using these rules that you can use the law of transmissibility in order to put vectors along, slide vectors along their line of action. You can only add like vectors. So in this case, we had the open head vectors and the closed head vectors. At this point, I'm going to turn off the image and turn off the open head vectors, and we're left with the closed head vectors. And I'm going to start adding them tip to tail. We do that by establishing essentially a line of action for each vector, or a line of influence, a line of action or a line of force for each vector. Then sliding the vectors. In this case, I'm going to go ahead and grab the vector and slide it from there to the intersection point. And do the same here. I'm going to now grab this vector and slide it so its tail emanates from the intersection point. But I'm not going to stop there. I'm going to take and go over here, and I want to realize that when we're doing that, it's not that we're actually moving it off of its line of action to just mathematically we are moving it, if you would. I'm going to put that there to the very end. And then finally what that means is we finally have a vector, and now we're going to go through that same process. We have a resultant vector. I'm going to take it. I'm hitting a control, taking this from the edge to there. And now I'm going to more or less set up a line of action, right? Because I'm going to go ahead and rotate this to this line of action, which is basically this vector is going to go from there to there, which means that this vector now, I'm going to go ahead and reestablish that again, a line of action from there to there. And now I'm going to take and go ahead and rotate this, if you remember, and we're going to see that we're going to do this all mathematically. We're going to rotate this from here to that same direction here, and then scale it. So I'm going to grab that middle scale point, and I'm zooming out here so it goes to where I want it to be. All right, so, and we have essentially what is the resultant of those two vectors here. We're going to get rid of that one. Right click, erase, and get rid of that one, because both of those effectively are now encompassed, and that means we can get rid of this one, erase, and get rid of this one, erase, and now what we have is these two vectors, which we're now going to add together again by once again establishing the line of action. And if you want to think about it from there to there, remember the line of action or the line of force works in both directions. We can now go ahead and slide this one to that point there. Didn't quite work. Try it again. What you're going to realize, you've got to grab the edge, because you cannot, if you otherwise you'll grab the construction line. We're going to go from here to the intersection point there. And you're going to do the same thing now with this one. You're going to grab it on the edge. You're going to slide it from here to there, and you're not going to leave it there because there is no point in cluttering your plane. And then finally you're left with the final resultant, and the final resultant is, I'm going to go ahead and erase that construction line and this construction line, and the final resultant then will be something that has that line of action. And now I'll just show you component-wise how you can bring things in another way, as instead of just doing the copies, you can then do window components and components, window components. You can grab in the model, unit arrow, we can bring it to there. And then right away we can rotate it, if we would, from there to there. And then S for scale, and we could just right away say 10. I think times might probably work, but otherwise we'll just grab this out. You want to grab, when you're doing the scaling on this, you want to grab it in the long direction, zooming out here, taking it awfully close. And it looks about right there. And so our final resultant by sliding vectors for what was the closed head vectors is that vector there. And so this is on, once again, on the closed head. And in the end, you will then go through that process for the open head as well. So the final adding of the components will be that there. You could have gotten this actual vector by just adding tip to tail in any way, shape, or form. But this vector not only has a point of application, a line of force and a magnitude and direction, it is going to really have an equal moment, and we'll do that separately to what we had started with. So that is what we end up with, which means this force can be anywhere along this line of action and be equal. Let's now turn back on the closed vectors and turn that one off. So we're going to go now through and add the open vectors, and it's the same process, isn't it? And so what you'll end up with is, in this case, a set of vectors that are one vector that is the closed head vectors and one is the open head vectors, and that then is your comparison. Again, I will do it on video, on a board, or on vellum. If you run out of paper, add more paper. The order that you add these things in does sometimes make a difference. So at this point, I'm going to go ahead and add just basically, I'll add the tough one. I'm going to add these two out because I now have the infinite plane. How do I do that? Remember, the line of action is infinite. So when I do that, that line of action goes in both directions. And when I go over here and I do the same thing, grab the endpoint there, grab that. Now I have that point of action right there. Remember, you slide everything so they emanate from their tail. You grab them off on the side because otherwise you're grabbing that line underneath. Clicking again, I'm clicking on that. I grab my basically my insertion point. I take it back to there. I'm going to do the same thing there. I'm going to grab that, move it from its endpoint to there, but then immediately I go ahead and just add it on top of this one. And in effect, we remember now that our new vector is going to have a direction. When you add those two together, the new vector is from there to there. And so we can once again put in a line of force. That is the new vector. In reality, you no longer need those. I'm coming across here, right-click erase. And however you want to do that, once again, you can bring in the unit vector to that point here. And then you can rotate that vector from there to there, back along there. And then you can S for scale and move that vector up to the point where it gets where it needs to go. And for all intents and purposes, you can now get rid of those two, and you're left now with this addition of two force vectors. Once again, it's always a good idea to establish the line of force, even though they do intersect right there. You've got that. You can move either one you care to, but you can go ahead and add this one, take that one. Remember to grab the vector, not the line of force. Grab that, move it from the edge there to the intersection there. Go back here now. Remember, when we do this, we are grabbing that. We're going to go from the back here, right? Slide it to there. That's what we're really doing, but mathematically then when we add them tip to tail. And then what we have in the end is our final result is, I'll do it one more time, bring in the unit arrow from there to there. We're going to rotate the unit arrow from there. Basically, it's a reference if you go back to here, back to that point there, and then finally the command is S for scale. Scale is this one there. You can grab the middle one, pull it to there, all intents and purposes, and you're left with then our final resultant. Looks like that. We'll erase this, and then we will establish a line of force for that. Now, because of layering now, we know that, in fact, we now have two resultant vectors. One is the closed head one, right? So if I go ahead, and that is the open head vector resultant, and in the end, that is the closed head vector resultant. And they're on two different layers. You've organized it and they should work. That they're at the same spot is just by chance or choice. Remember, you can move these vectors anywhere you want along that line of force, anywhere you want along that line of force, and it will be the same vector. And so a logical place to move these sometimes, if you're going to really be thoughtful about it, is to have them at the zero slope intercept. So I will do the same thing for the two of those. The zero slope intercept, I'm sorry, at the y-axis. So you can calculate the slope intercept and get all kinds of other kind of algebra math out of this. I'm going to go from here, once again grabbing the end, going down to the point where it is right here. And remember that when you end up with the resultant is going to be any equal force along that line of action. And so with that, you have the concept of sliding vectors, remembering that what's great about CAD is that you can organize things by layers, but you do the same thing on a plane by organizing by color. So vector quantities, typically you'll be adding forces only, but you could eventually be adding forces, accelerations, velocities, and positions on a vector field. So the fact that you can go through this, we will go back to this original vector add. We're going to save this now as vector add solution file, save as vector add solution, and then we're going to look at some of the animation aspects of why we put things in components here. So if I finally go with this, we'll do that to finish up this last 15 minutes. So I'm going to go ahead and I'm going to get rid of right now all the extraneous things that I have on here. I'm going to turn the images on, right? So you got the image, that's fine. And this is the vector solution, so I'm going to actually even get rid of the image. I'm going to take that and erase it. Remember, we have the original part here. Now let's look at what this looks like when I do a little programming and look for the transformation and whatever else. So what I'm going to do here is I'm going to close that up. I've got this on one layer, right click, entity info, that is closed head vector, right? And somehow I'm going to check, there is 3 in the model, I don't know. I am going to go and entity info, 3 in model, and I'm not sure where the other ones are, but I'm going to check. There's that little one floating down there because I drew it in the first spot. That's why now there are 2 in model. That was my unit vector. And now let's see what kind of data exists on these. Well, they each should have an insertion point that has 0 in the x and something in the y. They will have some rotation, and they will have some magnitude, which should be all tied into that 16 4x4 matrix. How can we look at that? Well, we won't look at it a lot, but we can go to the Ruby code editor, model, entities equals model dot entities. We have selection equals model dot selection, and you'll see me trying to keep these consistent. This is a Alex Schreiber's Ruby code editor. It's very similar to what you have from Jim Foltz. And then we have definitions equals model dot definitions, and then we have, remember, view equals model dot active underscore view, and then entities, we could do this, tran1 equals entities 0, right? And that's the first entity in the dot transformation. And then tran2 equals entities, and I should probably call that tran0. And this is tran1, so it's equals entities, entity, IES, I'm sorry, open the brackets, that's a list dot transformation. And just for grins, I can now say this, A O, which is going to be the matrix, equals tran 0 dot 2 array, and A1 equals tran 1 dot 2 array. And believe it or not, I know as we stack these things up that array at 16 places goes from 0 to 15. The 15th is always going to be 1. The 14th is going to be the Z. The 13th is going to be the Y. And the 12th is going to be the X. So my guess would be if I said this, put screen A0, 12, and put screen A1, 12, I should get 2 zeros coming out of that. We'll see whether that works. And essentially for this to work, we've got to do this. We've got to go back to Window, Ruby Console. Expect that when we go through there, the two things it's going to put out are going to be pretty much 0. And if you look at here, that could be basically how I drafted this, that these might not be as exact, and they're not. So let's see if I can pull that in. Click on that and use the move tool, which is M, and I'm going to grab that, and I'm going to really see if I can grab that. Once again, I'm going to pull this Ruby down. Grab that there. M for move, and I'm going to move that. It's probably not going to let me move it, so I'm not going to do that. You can see those two there. Let me see, instead of A12, let me look at A13 and A1, 13. That should be the Y component. As I run that, there they are. There's the Y component, 2.64 and 1.04. So you're going to see that there is some reasonable way for us to deal with pulling data out of this. An important piece of data, of course, would be the rotation. But the fact is that once you start getting involved in this, you open up the possibilities of not adding 3 vectors based on a like layer or like thing, but adding up 1,000 or 10. So once again, look at the general code here. I'm going to explain it and then be done. Model, sure. Entities, sure. Selection, sure. Definition, sure. View equals that. That's fine. And now finally I can go ahead and I'm going to finally show you a rotation of these two entities in a loop. And I'm going to do it this way. Tran rotate. So that's a transformation equals geometry, double colon, transformation with a capitalization, transformation dot new. I'm going to open my parentheses and first give it the point about which it's going to rotate. The second one is going to be the vector about what it's going to rotate, 0, 0, 1. And the third one is going to be the angle I want it to rotate, and I will put now capital PI / 12.0, which is, as you know, 15 degrees. And now I can say this for I in 1 dot 24. Entities dot transform underscore entities. The transformation tran rotate entities, the first entity, and entities the second entity. And remember, we start counting at 0. I've got this all laid out. Before I do that, I'm going to make sure I go File and Save. I've got my rotation there. I've kind of get this all set up so it can do a few different things. I've got the for statement. I'm going to keep going here, and I'm going to finish it out, see how much YouTube will tape for me. Now I'm going to say new view equals view.refresh, sleep 0.05, that's the time, and then end. And what you're going to see here is in a second it's going to probably rotate everything. And this you're going to see it's rotating about the 0.05 for its center point. It's straight up for its axis of rotation, and it's going to be rotating at pi over 12 because it takes things in terms of radians. And let's see how this goes. There it goes. Rotate it right around the circle. Try it again. And right and again. And you see it goes around each time as I go through. It's rotating fully around. Things go back to where they needed to be. And to make this change, of course, if I want to rotate about the x-axis, I could just change that variable there, come back to there, do the same thing. And we'll start talking about what that does. But now when I turn this around, it's rotating it around there. Rotating it around there. So this concept of transformations, rotations, all these different things, and how, in fact, however, the rule of doing things in 2D by sliding vectors is going to be a reasonable thing to get a good first quick solution, but you're going to see how quickly some of these skills and vectors kind of start to dovetail. Thanks for listening.